Hi there, and welcome to Raelene Math. Let's take a look at the basic discontinuous functions. I consider that there are 5 of them, and we can perform transformations on these functions to get more complicated or interesting functions that we can study. The thing that these 5 functions all have in common is that they have a domain of all reals except for 0, because they all have a denominator, and that denominator of x can't be equal to 0. We're going to take a look at the first graph in detail, the whole at x equal to 0. We also have a jump discontinuity, 2 vertical asymptote functions, one with odd symmetry and one with even symmetry, and then an oscillating discontinuity. So the first function is the basic hole in the graph, and we see that the x over x is a common factor, which we would like to reduce and set equal to 1. But if we consider the graph of y equal to 1, that's a continuous function. It's a simplified polynomial function of the form x to the exponent 0. And the domain of this function is all real numbers. Unlike this function, the x over x hole in the graph function doesn't allow x to be part of the domain, because when x is equal to 0, y is 0 over 0. And if we solve the equation 0y equal to 0, there are infinitely many solutions for y. There is more than one y value that makes this equation true. And so we call the y value indeterminate. And indeterminate is just a failure for the y-coordinate, really, to take on one single height. And so in the event that the function value is indeterminate, we are getting, but the height that y approaches from the left of the discontinuity and from the right is the same. So we call this a hole or a removable discontinuity. We can take a look at the graph of this function and see that if we were to trace along here, let's get tracing, that when x is 0, y is not a number. In fact, y is trying to take on an infinite number of different heights, like 0, 1, 2, 2.1, 2.2, negative 3.874. And as a result, we can't have more than one output for y when the input on the function x is a single value. And so we remove any possibility of y being 1 or any other height on the graph. We contrast that with the graph of y equal to 1, and the two graphs look the same. If I turn off the blue graph, we can just confirm that this purple graph doesn't have a domain restriction at x equal to 0. When x equals 0, y equals 1. So apart from that one single x coordinate, these two graphs are identical. And in fact, we do a lot of work with the reduced function, namely in this case the y equal to 1, except we remove the point where the hole occurs. Okay, let's take a look at a transformation of the basic graph. So the blue function, we could simply recognize that we have a common factor of x equal to x minus 2, which means that the domain is going to be all reals except for 2, and this tells us we have a horizontal translation. Rather, the fact that x has been replaced with x minus 2 tells us that we have a horizontal translation of the parent graph, the basic graph, of 2 spaces to the right. And so it gives us a new graph, which is the same horizontal line. We haven't scaled it or otherwise changed the graph. We've just moved the hole 2 spaces to the right. So we have a hole at 2, 1 on this function. The next graph is a little bit more interesting. First notice that we can factor the top. We get x plus 3 times x minus 2 all over x minus 2. And so here we can reduce the function. We could have also reduced the function here and called it x equal to, or y equal to 1, as long as x does not equal to 2. Going back to the red function, we can reduce and say that because the denominator can't be 0, x minus 2 can't be 0, and therefore x can't be 2. And so now this graph doesn't look like y equal to 1, it looks like y equal to x plus 3. So we draw that graph of y equal to x plus 3 with our x-intercepts, y-intercepts, and so on. And the graph of y equal to x plus 3 doesn't have any domain restriction. However, when x is equal to 2, this red graph would have a point at 2, 2 plus 3, which is 5. But the graph that we actually wanted to draw in the beginning doesn't allow x equal to 2, so we would remove that point and make it a hole in the graph. And that would be the graph of the given original function as opposed to the reduced function. And so we can see that the hole has been transformed according to the root of the common factor. Okay, the next graph we want to take a look at is the basic jump discontinuity. It looks a lot like x over x, except there's an absolute value in the top. We can also write the absolute value in the denominator, and it's not going to change overall. We go back to the definition of the absolute value of x, which is either negative x if x is negative, or just x if x is non-negative. We can generalize this for any stuff inside the absolute value and say that the absolute value will either change the value of stuff, rather change the sign of stuff, by multiplying by -1 if stuff is negative, or the absolute value can be removed and do absolutely nothing to the stuff in the case that the stuff is non-negative. So if we take the absolute value of x and then we divide by x, we can see that our function is going to have a domain restriction that x can't be equal to 0 because the denominator cannot equal 0. And furthermore, we will have a simplified function of either -1 if x is less than 0 or +1 if x is greater than 0. And so we tend not to include any function value when x is equal to 0 here. So we can take a transformation of this jump discontinuity by looking at some new functions. Let me just point out on this graph, as x approaches 0 from the left, y approaches a height of -1, and as x approaches 0 from the right-hand side, keep in mind that x equal to 0 is the equation of the y-axis. So as x approaches the y-axis from the right-hand side, y is approaching a height of +1. So these are two finite heights that y approaches. So we have a left-hand limit, or a left-hand height of -1, and a right-hand height of +1. These two values are finite but different, and therefore the overall limit at x equal to 0, the single finite height that y approaches as x approaches 0, we say it doesn't exist. All of that information is summarized at the end of the video on a slide. Let's take a look at a transformation of the basic jump discontinuity. In the first function, we want to put it into transformational form, which involves some factoring. I can factor a -3 out of the top, and I can factor, well, I don't need to factor, I've got the absolute value of x minus 2 in the bottom. We can see that we have a common factor of x minus 2, which means that we're translating again horizontally 2 spaces to the right. So we expect our jump discontinuity to occur along the vertical line of x equal to 2. Now, one thing we could do would be to let a new variable like t equal to x minus 2. And we would come up with a new graph of -3 times absolute value of t over t. And so here we would only need to worry about the vertical reflection and the vertical scaling. So instead of going to a height of 1 or -1 for the jump, we would be going to a height of 3 or -3. And this t is really t minus 0, and so we're ignoring the horizontal translation and taking the jump back to the t equal to 0 or vertical axis of the y-axis. So now all we have to do is reflect the graph. So instead of being positive and negative like this, we would swap them, vertically reflect, and they would be at the heights of 3 or -3 instead of the heights of 1 or -1. So we could do this for a new t variable, but we could go back and put it into the blue graph by saying the horizontal translation tells us that the jump occurs at x equal to 2 instead, with the same heights of 3 or -3. And so we would get the blue graph looks something like this, with the jumps at 3 or -3, as I said. Okay, so another possibility is a graph that looks a bit more complicated than just a linear factor inside. And the first thing I'm going to do is factor as much as possible. Let me just clear that. So let's say we've got y is equal to the absolute value of x squared times 2x minus 1. We're starting to see that common factor of 2x minus 1. And we can apply the property of absolute values to the numerator. If we consider what the absolute value does to a function, we can understand the graph of y equals the absolute value of x squared. We can start off drawing the x squared graph, and I'm going to draw that as a blue graph. The x squared graph looks like this, and the absolute value of any y values reflects vertically. It's a partial vertical reflection, but this blue graph is already completely above or on the x-axis, so the absolute value does absolutely nothing to the blue y-coordinates, and the absolute value of x squared is the same as x squared. You can take a look at the graph if you don't believe my hand drawing of it. If we have y equals modulus or absolute value of x squared, it's exactly the same as the inner function. Okay, so then what's happening over here is that we can replace the absolute value of x squared with just x squared, and we can see the same kind of plus or minus 1 jump discontinuity behavior happening. But now we don't have a horizontal translation of 2 because our common factor of 2x minus 1 has a different 0. So we'd find the 0 or the root of that factor by setting the factor equal to 0, and we can see that the root is x equal to 1/2. So our jump is going to occur now at x equal to 1/2. You could do a substitution like we did over here, let t equal the common factor, and then we could take the transformed graph and we can kind of ignore the horizontal translation and just put the jump, as it were, back at the origin or on the y-axis. I'm not going to do that. I'm going to draw the graph with the jump occurring at x equal to 1/2. But the difference here is, maybe before I should draw the graph, let's remind ourselves that we had this bubbled piece was either plus or minus 1, depending on whether this stuff was positive or negative. And so as a piecewise function, this is going to be x squared times negative 1, which I can just write as negative x squared, when the stuff inside the absolute value, which is 2x minus 1, is less than 0. But if 2x minus 1 is less than 0, then x is less than 1/2. So I'm just going to write that as x less than 1/2. Meanwhile, the bubble will be positive 1 times the x squared, which is just x squared, if the stuff is positive, meaning if x is greater than 1/2. Recall that the denominator can't be 0, that's why we don't have an equal to for x equal to 1/2. So this graph is a piecewise absolute value graph, and I can draw the vertical line of x equal to 1/2 quite lightly, just to remind me where the two pieces change. And so I'm either going to get the graph of negative x squared, which looks like this, or the graph of positive x squared, which I'm not actually that good at drawing it without doing the whole parabola, and so it does something like this. And so the jump behavior is really occurring in here. It doesn't matter what's happening elsewhere on the graph. We're really focusing at the region of x equal to 1/2, and we're getting the jump discontinuity. We can see that there are two different heights, and they're both finite heights. And the left-hand height, if x is 1/2, then negative 1/2 all squared would be negative 1/4. Meanwhile, the positive, or the right-hand side of the jump is y equal to a height of positive 1/4. So as x approaches 1/2 from the right, y approaches a positive 1/4 height, and as x approaches 1/2 from the left, y approaches a negative 1/4 height. The next two parent discontinuities we're going to look at are really the same type, a vertical asymptote, but there's going to be two different kinds, an odd type and an even type. In this function, if we evaluate the y-coordinate when x equals 0, which is not part of the domain, we get that y is equal to 1/0, which is a case of being non-zero over 0, which means that the y value is infinite. In other words, we're saying that as x approaches a 0 value, a finite number, which is the vertical line of the y-axis, then y either approaches positive infinity or negative infinity. And so to find out which sign, positive or negative, from the infinity that y approaches, we could really make a sign chart or draw the graph completely. So anytime that a finite x value makes y infinite, we have a vertical asymptote. Now this type of 1/x is called an odd type because this basic function has odd symmetry. And odd symmetry means that when we perform a horizontal reflection on the function by substituting negative x for x, that we end up getting negative times the function, which means it's the same graph as if we had performed a vertical reflection. So anytime we perform a horizontal reflection and the graph looks like it would have if you performed a vertical reflection. We call that odd symmetry. And so as a result, I'm referring to this parent function as having odd vertical asymptote behavior. Specifically, as x approaches the vertical asymptote, or the line x equal to 0, which is the discontinuity x-coordinate. As x approaches 0 from the right, y shoots up and approaches positive infinity. As x approaches 0 from the left, y shoots down and approaches a height of negative infinity. And so this one of each behavior, positive infinity or negative infinity, is the characteristic of the odd type. Now the next type is the even type, and this is the reciprocal square function. Obviously, if we square a value and reciprocate it, we're not going to get any negative values, and so a sign chart would tell us that we don't have any y-coordinates that go to negative infinity, for example. So in this case, when x approaches 0, 1 over 0, or non-zero over 0, is only going to give us positive infinity because we can't get any negative y values in the range of this function. So I refer to this as an even type because in this case, substituting x with negative x and performing a horizontal reflection gives 1 over negative x all squared, which is 1 over x squared, which is the same as the original function. So anytime a horizontal reflection of a graph produces the same as the original function, we have even symmetry, which means that the function has the y-axis, or the line x equal to 0, as an axis of symmetry. Cuts the graph into two equal halves, right and left. But specifically for us, in this case, as x approaches 0 from the right, y approaches only positive infinity, and as x approaches 0 from the left, y also approaches positive infinity. So we have slightly different behavior, but we still have a vertical asymptote because a finite value of x makes y infinite. To see some transformations of the basic vertical functions, take a look at some of the rational function videos, graphing rational functions, etc. There's a lot of good information there that really helps to lay the foundation for understanding limits in calculus. The last basic or parent discontinuity is the oscillating discontinuity. And to start off understanding this, let's consider the graph of y equals sine of x. This, let's only look at it from the right-hand side. It does the same on the left. In fact, the sine graph has odd symmetry, so you could rotate this graph 180 degrees about the origin, and you would get the rest of the graph. Okay, I'm just going to move that out of the way. When we talk about oscillation, we talk about something that repeats. A fan oscillates because it goes around and around. A pendulum oscillates because it swings back and forth from start to furthest away point and back again. A sine graph oscillates because it takes on all the y-coordinates from a minimum height of -1 to +1. And so on this graph, as x approaches positive infinity, the y-coordinates never really settle on one height. The y-coordinates keep going down to -1, all the way up through the negative values to 0, through positive values up to +1, and back and forth. And it does this infinitely many times as x approaches infinity, just up, down, taking on more than one value, an infinite number of heights, from a minimum height of -1 to a positive height, to a height of +1. And so we say that as x approaches infinity, the y-coordinate on the sine graph, it doesn't exist because the y does not approach one single, let me write that, y doesn't approach one single finite height. It approaches infinitely many heights that are from -1 to 1. And so we say that y does not approach a single finite height, so the y-coordinate or the sine x coordinate doesn't exist. What we talk about then for an oscillating discontinuity is different from when we talk about end behavior, because discontinuities don't occur at the ends when x approaches positive or negative infinity. Discontinuities occur when x approaches a finite number. And so in this case, we see a discontinuity or a domain restriction for x equal to 0, and as x approaches 0, y approaches, well, going this way on the graph, y is trying to take on all of the heights from +1 to -1, up and down, infinitely many times. And so y doesn't approach one single height, y approaches an infinite number of heights, just like the inside-out view on the sin x graph does. To understand the relationship between the oscillating end behavior as x approaches infinity on the sin x graph and the oscillating discontinuity as x approaches 0 on the sin 1 over x graph, check out the inside-out reciprocal transformation video. To summarize the 5 basic discontinuities, here's a rule of 4 overview, and you can take a screen snapshot of this and read it at your leisure. We look at the functions using an algebraic, a graphical, a numerical, and a verbal approach. If you learned something in the video, tell your friends, tell me in the comment section below, like the video, and subscribe to my channel. Thanks for checking out Raelene Math.